In the previous video, we showed how to derive Abel's formula. So in this video, what we're going to do is we're going to show how Abel's formula can be used to derive the reduction of order formula. So what we want to do is we want to solve this first order ODE in W for W. So to do that, what we're going to do is we're going to bring all of the W's to one side and then integrate. So if we divide both sides of this equation by W, we get W prime of x divided by W of x, and then that's equal to minus P of x. So now what we're going to do is we're going to integrate both sides of this differential equation. So I'm going to integrate from a lower limit of x0. x0 here is just some constant, and the upper limit is going to be x. Now, because I'm using x for my upper limit, in my integrands, I'm going to have to replace x with some dummy variable. So in the integrand, I'm going to replace all of the x's with u's. So in this case, the left integrand, that's just going to become w prime of u divided by w of u du. And then the right hand side is going to be, again, the integral from x0 to x of p of u du. All I've done is just replace the x's in the integrand with u to avoid confusion with the upper limit. So if you look at the left-hand side here, the integrand on the left-hand side, you'll notice that this w prime over w, well, that's just the derivative of log of w. Okay? So w prime over w, that's just the derivative of log of w. So we can write the left-hand side as the integral from x0 to x as the derivative of log of w. And the right-hand side stays as is, integral from x0 to x of p of u du. So here, the advantage of writing the integrand as the derivative of log of w, now we have an integral and a derivative, which of course will cancel each other out. And the left-hand side will be left as log of w of u, but then we have to evaluate that from the lower limit of x0 to x. And the right-hand side, again, stays as is. So the left-hand side here, that will evaluate as log of w of x minus log of w of x0, which of course can be rewritten using log rules as log of w of x divided by w of x0, and again the right hand side stays as is. So our goal here is to solve for w of x. To do so, we have to exponentiate both sides. So if we exponentiate both sides, the left-hand side will reduce to w of x divided by w of x0, but then the right-hand side will reduce to e to the power of the integral from x0 to x of p of u du. And then we can just multiply both sides by w of x0 to solve for w. So w of x is w of x0 times e to the power of minus x0 to x of p of u du. Now here, this lower limit x0, x0 is just some constant. So if we evaluate this limit, if we evaluate this integral, we'll be left with some function in x minus some constant. So in other words, you can strip out the contribution of the lower limit and just tack it on as a constant. Specifically, we can rewrite the right-hand side as w of x integral to x of p of u du, and then plus some constant. So you can strip out the contribution of the lower limit and just tack it on as a plus constant. And then we can rewrite this exponential term as e to the power of some constant times e to the power of the integral. And of course, x0 here is just some constant. E to the power of some constant is as a constant. So these first two terms here, they're all just one constant. So let's just call them A for the sake of notational simplicity. In other words, w of x is just going to be A times this exponential term. So let's just transcribe that on the next board. So we have w of x is equal to A times e to the integral x of p of u du. So recall that our goal here was to derive the reduction of order formula. So to derive that formula, we need something in the form y2 equals. So we really want to solve for y2. Here, there are no y's in the equation. So how do we get y's involved in this equation? Well, recall the definition of w. W is just y1, y2 prime minus y2, y1 prime. So we've gotten y2 into this equation. So what we want to do now is we want to solve this equation for y2. Now how are we going to do that? Well, to do that, I'm going to do something that may seem a little strange at first. I'm going to divide both sides of this equation by y1 squared. So I'm going to divide both sides of this equation by y1 squared. So why am I doing that? Well, if you look at the left-hand side now, notice that you can write it as ddx of y2 over y1. So you can write it as the derivative of a quotient. So if you work out this derivative, you'll get y1 y2 prime minus y2 y1 prime over y1 squared. Just standard quotient rule from single variable calculus. But notice that's exactly what we have here on the left-hand side. So we can write the left-hand side as the derivative of y2 over y1. So why are we doing that? Well, we're doing that because if we integrate this equation now, the integral and the derivative will cancel each other out. So that's why we want to write the left-hand side as the derivative of some quantity. So if we replace the left-hand side with the derivative of y2 over y1, and then the right-hand side stays as is, a over y1 squared times e to power of integral to x of p of u du. Okay, so what we're going to do now is, because we want to solve for y2, we want to get rid of this derivative somehow. So to get rid of this derivative, we can integrate both sides of this equation. So specifically, we're going to integrate both sides again from x0 to x. And because we're using an upper limit of x, we're going to have to replace the x's in the integrands with dummy variables. So this left-hand side, we're going to replace the x's with t's. So just a second dummy variable t. And then this left-hand side is going to be the integral of ddt of y2 t over y1 of t. t. Okay, so all I've done here is just replace the x's and the integrands with t's, just to avoid confusion with the upper limit. And then the right-hand side, again, we're going to integrate from x0 to x, and then we have to replace all of the x's and the integrands with dummy variables. So that becomes a over y1 of t squared times e to the power of minus the integral. Well, the x here we're going to have to replace with t. So that's the integral to t. And then the u's again we can leave as is because they're already dummy variables. And then this entire thing is being integrated with respect to t. And because we have an integral and a derivative, they will cancel each other out. Specifically, we can write the left-hand side as y2 of t over y1 of t, but we have to evaluate that from an upper limit of x and a lower limit of x0. And the right-hand side, we're just going to leave the right-hand side as is. The integral from x0 to x of a over y1 of t squared times e to the integral to t of p of u du, and then that's all dt. The left-hand side here, well, if you work this out, you'll get y2 of x divided by y1 of x minus, well, you'll get minus y2 of x0 divided by y1 of x0. But because x0 is a constant, y2 of x0 over y1 of x0 will also be a constant. So for the sake of notational simplicity, we can just call that second term, let's just call it b. It's just some constant. So we're just going to call it b for the sake of notational simplicity. Now the right-hand side here, so as we did before, we can strip out the contribution from the lower limit and just tack it on as a plus constant. Specifically, we can write the right-hand side as the integral to x, and then everything in the integrand stays as is. The only difference is that we just add on some constant. Let's just call it c, okay? So we've just stripped out the contribution from the lower limit and just tacked it on as a plus some constant. So what we want to do is solve this equation for y2. So to do that, what we're going to do is we're just going to bring this b over to the right-hand side and then multiply both sides of the equation by y1. So let's do that. So I'll just transcribe the last equation we had there. So we had y2 of x divided by y1 of x, and minus b, and then we had the integral to x of a over y1 of t squared times e to the integral to t of p of u du dt, and then we had plus c. And of course, a, b, and c here are constants. So what we're going to do is we're going to bring the b over. So if we bring the b over, we get y2 of x divided by y1 of x is equal to the integral to x of a over y1 of t squared times e to the integral to t p of u du dt. And then we're going to be left with b plus c. Plus b plus c. And of course, b and c are constants. So again, we can just call b plus c another constant. Let's just call it d for the sake of notational simplicity. here, we can multiply both sides by y1 to solve for y2. So if we do that, we get y2 of x is equal to y1 of x times the integral of x of a over y1 of t squared times e to the integral to t p of u du. And that's dt, and then plus d. And then that's all going to be a square bracket. Okay. Now here, y2, we only want y2 to be linearly independent from y1. So it doesn't really matter what the values of a and d are, because all we want to do is generate a second linearly independent solution. So for the sake of simplicity, we can just take d to be equal to 0. So we can take d to be 0. Now, you can also take a to be 0. But if you take a to be 0, then you'll just get y2 is equal to y1 times 0, which is 0. And 0, again, it's not linearly independent from y1. So we take the next simplest number, which is 1. So specifically, we take d equal to 0 and a equal to 1. So if we do that, the formula reduces to y2 of x equals y1 of x times the integral x of 1 over y1 of t squared times e to the integral to t of p of u du dt, which of course is the familiar reduction of order formula that we wanted to derive in the first place. So in the next tutorial, we'll show how this formula can be used to solve linear second order homogeneous ODEs. Specifically, we're going to guess one form y1, and then we're going to use this formula to find a second linearly independent solution.